to record it so we have it later if we need. Voila. So now let's continue the course. So I'm taking it on page 17, and on page 17 we have a small exercise. Did I give it to you to do or not? Ah?
No, he just told us to like it.
Okay, so let's do this exercise. We can do it together. Anyhow, you have the correction here. Okay, so let's do it separately and see what we can learn from that exercise. The exercise is about two spies who are stealing a safe. Okay, so you see the two spies, they are stealing a safe and they pull the safe in different ways. So if we take the problem statement, okay, we have these two spies, we have a safe, and the mass of the safe is 225 kilograms. Okay. The safe is displaced over a distance of 8.5 meters. So the distance is 8.5 meters. Okay, and then we say the push F1 of spy 01 is 12 newtons, directing at an angle of 30 degrees downward from the horizontal. So here we have spy number 1 who is pushing this safe in this way, okay, with an angle which is here, what did I say, 30 degrees?
Yes.
30 degrees. Okay, and the second spy is pulling the safe with a force. And here I didn't write the intensity, it's 12 newtons, and the second spy pulls the safe with a force of 10 newtons directed 40 degrees above the horizontal. So here we have 10 newtons and here we have 40 degrees. Okay. Question A is, what is the net work done on the safe by the forces F1 and F2? So now we want to know the work done by the forces F1 and F2. So how would you compute that? Let's start with the work for the force 1. Okay? You remember that the work is the scalar product of the force with the distance, and this you can write as the norm of F, the norm of D, and then the cosine of the angle between F and D, right? So for the work of the first spy is going to be F1 times D, and how do we write this? The norm of F in that case it's 12 newtons. The distance is 8.5 meters, and then we have the cosine of the angle, which is 30 degrees. Actually, if you want to be precise, you can say minus 30 degrees. It doesn't change anyhow, because the cosine of 30 is equal to the cosine of minus 30. Okay? And so we can compute that. The cosine of 30 is 1/2, and if you compute that quantity, you get 88.33 joules. Okay? Okay. Now the work due to the force of the second spy is going, of course, to be F2 times D. So it's the norm of F2, etc. The norm of F2 is 10 newtons. The distance is the same, and now we have the cosine of 40 degrees. Okay, and if you compute that, I'm using the results in in the course. Okay, I'm not computing them with my calculator because my calculator is my phone, and my phone is used as a webcam. I cannot. And I discovered that I don't have a decent calculator at home, and I cannot buy one now. Okay, so what is going to be the network? Okay, the network done by these two forces, what do you think? Does it add? Does it subtract? What do you think?
It's adds.
Sorry?
Add.
Yeah, you should add because the two spies are pushing in the same direction. So the network is going to be work 1 plus work 2. So it's going to be 88.33 plus 65.11, and that is approximately 153.4 joules. Okay? Okay, so now we have question B. Okay? Question B, during the displacement, what is the work WG done on the safe by the gravitational force, and what is the work WS done on the safe by the normal force? Can you, let me just do a drawing. Okay, we have our safe here, we have the two forces of the two spies, and then we have the gravitational force which is pointing downwards. Okay, we have the normal force which is pointing upwards, and we have the displacement which is horizontal. So what would you say about the work of the gravitational force without doing computations? What would you say about that?
So we do like the mass of the cell times g, and then yeah, I don't know.
So you mean you take the norm of Fg times the distance, the norm of the distance, times the cosine of which angle? What is the angle here between Fg and the displacement?
Oh, it doesn't work, right?
Yeah, it works, but
it does. It does not affect the, I don't know.
well, you have a cosine of 90 degrees because you have an angle of 90 degrees between the displacement and the force, okay? And the cosine of 90 is 0, okay? So the work of the gravitational force here, it's 0, okay? And this is something you could have guessed right away because the gravitational force is perpendicular to the displacement, so it doesn't do work on the displacement, okay? It's just there, but it doesn't do work, it doesn't influence the motion of the safe, it doesn't accelerate it or decelerate it, okay? So now the work of the normal force, what do you think it is?
0, 2.
Yeah, it's 0, 2. Actually here I should have said maybe cos minus 90, and here we will have a cos of 90, which is also 0. So the work of the forces which are perpendicular to the motion, the work is always 0 in that case. Right? Okay, now we have a question C. I don't know if you see these questions. Sometimes you need to look for the questions. This is question A. This is, where the hell is question B? This is question C. Yeah, sometimes you need to look for them. Oh yeah, B is here. Okay, so we did B, now we have to do C. The safe is initially stationary. What is the speed Vf at the end of the 8.5 meters displacement? Okay, so question C, we have our safe which is moving. Here it's initially at rest, okay, and after some time, as an effect of the push, it's moving with some velocity, right? Because we consider that the flow is frictionless. Okay, so the force that is exerted by the two spies, it will accelerate this system. Okay, and so the question is, what is the speed Vf at the end of the 8.5 meters displacement? Okay, so what we are going to use now as an equation to solve that is the equation which tells you that the difference between the final kinetic energy and the initial kinetic energy is just the total work. You remember that? I'm sorry, my camera disconnected. I don't know why. Sorry? Yeah, wait, it's going to reconnect. Sometimes it disconnects. I guess it's because the cable is not good. I don't know. Oh, God. Let me see if I can do something. Okay, so instead of connecting the camera with the in USB, I connected in Wi-Fi and it works. Okay, this is an important relationship. Okay, and this W, actually you could write it as motor work plus friction work. Okay, and you remember that motor work is positive, friction work is negative, but in our case we have only motor work because the spies are pushing. Can you see now properly or not?
Yeah, we can see properly.
Yeah, but there is a delay of a few seconds. It's a mess. You see, I'm now standing and this thing is still. So let me put it back to USB. And yeah, like this, you see my hand in real time. Oh God, I'm tired of all these technical problems. I spent last week.
Mamma mia.
Yeah, mamma mia! Don't make fun of me. I spent most of last week ordering devices on Amazon to improve my internet connection, because I live in the countryside in France and it's a mess here. My normal connection, my Wi-Fi, was 2 megabits per second. Okay, so I had to buy a 4G modem, and now I also ordered an antenna to point it to the network antenna to improve the speed. It's a mess. Okay, so we are going to use this equation, and in this equation now, if we write it in a more specific way, the final kinetic energy is 1/2 mvf squared. I'm just applying the formula. Okay, the initial kinetic energy is 1 times mvi squared, where vi is the initial velocity, and that is equal to the work. So it's the total work. It's work 1 plus work 2. Okay, this is pi 1, this is pi 2. Okay, we agree with that? Okay, then we know that the initial velocity is 0, right? And so now we can compute the final velocity as a function of all the rest. We can solve this equation for Vf. Okay, and so we have that Vf squared is equal to 2, because I'm multiplying by 2, divided by m, times work 1 plus work 2. This would be Vf squared. So if I have Vf, I need to take a square root. Is this okay? Okay. And so now we can compute. It's 2 over the mass is 225. Okay, and this is times W1 plus W2, which we computed just before, and the sum of the work for the two spies was 153.4. Okay, and if you do this calculation, and I will trust the result in the book, it's 1.17 meters per second. Okay? By the way, this equation that we wrote here, does it recall you an equation that we saw when we did kinematics?
Yes,
Mm.
but I don't remember the name.
Oh, the last one.
The what? You don't remember the name? Sorry?
The velocity equation?
No. Look at it.
Torricelli?
Torricelli. Okay, this is actually Torricelli. Why is it Torricelli? Because you see, I'm going to multiply by 2 over m, okay, so that I can get rid of these factors 1/2 of m here. I multiply everybody by 2 over m. So I have Vf squared minus Vi squared is equal to 2 over m times the work, but the work is the force times the distance. Okay? And now the force over the mass, it's the acceleration. So what you get on the right hand side, it's 2 times the acceleration times the distance. And this is Torricelli. Okay?
That would translate properly.
Ah, sorry. This is Torricelli. You have the final velocity square minus the initial velocity square equals to 2 times the acceleration times the distance. This is just Torricelli. Okay? So Torricelli has an interpretation in terms of kinematics, but it also has an interpretation
Yeah,
in terms of
let it back.
energy. Sorry? Ah,
Yeah, just leave it like this
yeah, yeah.
for 2 seconds.
Tell me when I can continue.
Oh, it's okay.
Okay, good. So now let's continue and let's point our interest at the gravitational force and the work it does. Okay? In the case of the safe, we saw that if we are moving horizontally, the gravitational force does not do any work. Because it's perpendicular to motion. But in the case where we go up and down, of course, the gravitational force is going to work in that case. Okay? So let's assume we are moving up. Okay? This is the displacement. We are moving up. The gravitational force is going down. Okay, as usual, it's direct downwards, and we have a velocity. We have an initial velocity, a final velocity. You see here they have drawn these little boxes showing that the kinetic energy is decreasing. Okay, of course it's decreasing because the velocity is decreasing since you have a force which is acting downwards. So what is the work done by the gravitational force in this case? It's here, right? We know this formula. You understand where this formula is coming from? This mg is just the gravitational force, and so the work of the gravitational force is the force times the distance times the cosine of the angle, right? Now, how much is the angle? You have to be very careful about that. You have the gravitational force which is going downwards, and you have displacement which is going up. Okay, so the
180?
Exactly. So the angle is 180, and when you compute with the cos of 180, we have this work of the gravitational force, which is mgd. Okay? Actually, you will see that at some point we will define the potential energy as mgh. So you will see this is connected to the potential energy. We will get there in a moment. One thing that I would like to clarify is that when you compute the work, you have to decide for which force you compute the work. Okay? For instance, if I take the example where you are taking an object and you are raising it in the gravitational field, okay? You are raising it. What happens? You have two forces acting, okay? You have one force, which is the gravitational force, which is pointing downwards, but you have another force, which is pointing upwards. What could that force be? What do you think? This force which is going up, what is it?
Net force.
No, the net force, it's going to be the sum of the two. Again, I do the experiment, I lift. Oh God.
Yeah.
Ah, please. And I tried to buy a new webcam on Amazon, and it's empty. There are no more webcams in the stores. Oh, let me see what.
Happy birthday, Mike.
Was birthday?
It's my birthday.
For some reason, the software which connects the cam stopped. I don't know why. Okay, so if I am lifting this object above the ground, there is one force which is going downwards, which is the gravitational force, but there is one force which is going up, which is the force I am transmitting with my hand to this mouse to lift it. Okay, I'm also exerting a force, and so these two forces which we have here are, one of them is the gravitational force, and the red one is the force that I am giving, I am applying to this object. Okay, and so now if we have an upward displacement, like here, okay, the gravitational force, it does negative work because the angle is 180 degrees, but the force that I am exerting on the object, this force is doing positive work because it's in the same direction as the displacement, right? And now if I go down instead, if my displacement is going down, what is going to happen? The gravitational force is going to do positive work on the system because it's going in the same direction as the displacement, whereas, sorry, I used the wrong colors. So the gravitational force is doing positive work, and the force which is directed up, this would be the force with which I'm holding the object, and then I let it go down. This force is doing negative work in that case.
I just have a question.
Yeah.
Si on met le repère dans le sens du mouvement pour le premier, on est obligé de le changer quand ça redescend?
No, why? What do you mean? Aha, you mean if an object goes up and down again?
Yeah.
Okay, you mean we have an object, it's going up and then it's coming down. Okay, when it's going up, we have the gravitational force which is pointing down, and the force of your hand, let's say, which is pointing up. And when you bring it down, again, the gravitational force is going down, the force which you exert on the object is going up. So the forces, they don't change. Actually, this is what you see here also. Fg is always downwards, F is always upwards. Okay, so actually in this situation you have the two cases which are here in the course. Okay, when it goes up, it's this situation. When it goes down, it's this situation. I don't see exactly why you want to change the reference frame. What changes is the direction of the displacement. Okay, but you can very well use the same reference frame for the two cases.
No, I meant like, vous savez, le point de repère, genre dans cette direction c'est positif, quand ça redescend c'est négatif.
In this case, we don't have that kind of problem. Here, what changes the sign is the angle between displacement and the force. Okay? In this case, the work is the force times the distance times the cosine of the angle. And so this force here is doing negative work. This force is doing positive work when we go up. And when we go down, this force is doing positive work and this force is doing negative work. Okay? Good. So be careful. This is something I'm telling you. It's important when you compute work. Ask yourself for which force you do compute the work. Okay? Because if it's the gravitational force or if it's the force with which you lift an object, it's not the same. Okay, we are going to do another exercise. It's about an elevator, and this elevator has a cable which slips, so it stops going up, it goes down, but the cable slips, but it's not completely released, so it slows down the cab. Let's read the problem. An elevator cab of mass 500 kilograms. Well, you have the course anyhow, so let me write it here. Maybe it's a bit big. Okay, so we have an elevator cabin. Okay, the mass is 500 kilograms and it's descending with an initial speed of 4 meters per second. This is the initial situation. Okay, and in this initial situation the supporting cable begins to slip. You understand this word, to slip? Le câble se met à glisser et donc l'ascenseur va descendre plus vite que ce qui est prévu. Okay? Allowing it to fall, and so the cab falls with a constant acceleration which is g over 5. They tell you A is equal to g over 5. Since g is pointing downwards, A is also pointing downwards, so we have this acceleration here which is pointing downwards. Okay? And the acceleration is g over 5, so it's about 2.5 meters per second square. Okay? The acceleration is approximately 2.5 meters per second square. Okay? Now, what are the questions? Question A is during the fall through a distance of 12 meters, what is the work done on the cab by the gravitational force? So I let you do it, try to do it, and then we restart in, I'm going to be here and I will correct it in 2 minutes. Try to do it. Try to compute the work of the gravitational force. I'll let you do it. what I forgot to say is that the distance on which it falls is 12 meters, but you see it in the problem statement. Okay, did you do it?
No.
I mean, you have the correction, but don't follow the correction.
Shall we use 9.81 or 10 for G?
981. Actually, in this book, if you notice, they use 9.8. You realize that? They don't use 9.81. And why is that? It's because the average G over the US is more like 9.8 than 9.81. And so all the Anglo-Saxons, they use 9.8 as gravitational acceleration, whereas in Europe we tend to use 9.81. Okay, can I correct? So the work is going to be the intensity of the gravitational force times the distance times the cosine of the angle. What is the angle between the gravitational force and the displacement? Okay, we know that the displacement is pointing down and it has a norm of 12 meters. So what's the angle now?
180.
No, the gravitational force is pointing down and the displacement is pointing down, so it's 0. Okay, so this guy is 1, and so the Fg times d is m times g times d. Okay, and the mass we said is 500, g is 9.81, and d, the distance, is 12 meters. And if you do this calculation, it gives you 58. Well, they say 59 here. It's 58.8. It's 5.88 times 10 to the 4. So okay, let's keep it 58,8 times 10 to the 3 joules, and this is 58.8 kilojoules. Okay?
I can't read what
You can't read?
58.8.
Yeah, I corrected it. This is 58.8 times 10 to the power 3.
Oh.
Yeah, sorry. This is nothing. I don't have one of these erasers here. Okay? Let me see if I have. No, I don't have one of these erasers. Okay?
Is it a 4?
What?
Like 58.8 times 4?
No, times 10 to the power 3.
Yeah, underneath. KJ?
It's kilojoule.
Or, okay, yeah. Thank you.
Okay? This is the work that the gravitational force is doing on the cab during this 12 meters. Okay? Now, question B, we are going to read it together, and then you are going to do it by yourself. So the second question is, during the 12 meters fall, what is the work Wt of the tension which is acting on the accelerator? So the accelerator, it has two forces acting on it. We didn't talk about tension yet. There is the gravitational force which is pointing downwards, and there is the tension in the cable which is pointing upwards. Okay? And the gravitational force is of course a bit bigger than the tension. Why? How do I know that? How do I know that the gravity? because it's falling, because it's accelerating downwards. Okay, and if we have an acceleration downwards, it means we have an excess of force downwards. Okay, so we should expect T to be smaller than Fg, otherwise it's going to be a mess. So now, of course, if you want to compute the work of the tension force, is going to be the norm of the tension times the norm of the distance times the cosine of the angle between the tension and the distance, which is how much, by the way? I recall you that the distance on which the accelerator falls is this. Well, draw your vectors. Now the tension is up, the distance is down.
It's 180.
So the angle here is 180, right? And so this amounts to minus T times D, because this gives you minus 1. What's going on? What's going on? Okay, whatever. So now what you need to do, until here we could go, but now you need to compute what is T. Okay? And so what we know, we need to compute T. What we know Fg, and what else do we know which can help us to compute T? What's the other thing we know? We know the acceleration. We know the acceleration, right? And so if we want to compute T, knowing Fg and the acceleration, which law should we use, you think? Which is the law that connects all the forces acting on the cab with the acceleration?
F equals m times a, and r equals to f1 plus f2.
You say F is equal to m times a, and what else did you say?
F net equals to f1 plus f2.
What is F1 and F2?
All the two forces that act on the body.
Yeah, but we gave them a name, okay? These forces are Fg, so the net force is Fg plus T, okay? So indeed, this is the second Newton's law. This is what you should use to compute T, okay? I recall you the second law of Newton. It is the sum of the forces is equal to the mass times the acceleration. Okay? So now I let you do the calculation. You use the second Newton law, and with that you try to compute T. I let you do it. I will let you do it for 3 minutes. I need to go to the toilet. Okay? You don't mind? Okay, thank you.
Les gens, on peut chanter Joyeux anniversaire pour Santiago.
3, 2, 1.
Joyeux Ouais, c'est marrant, ça lag.
Tout le monde t'a capté là-dessus. Mais c'est pas grave. Ça lag en quarantaine, ça pique. Ah, c'est trop chelou. Là, j'aurais pas
Pour mon anniversaire, j'ai dû me réveiller tôt pour un cours de physique. C'est par hasard. C'est le jour où il y a un cours. J'ai 17, arrête, j'ai 17.
Eh les gens, je vous dis, on va comme douce musique.
Ouais, je suis un peu comme...
C'est un gros agacement.
Je me suis réveillé ce matin avec plus de poils. Je vous dis pas où, hein, c'est que...
Ah, non, regarde pas ça.
C'est moi ou Maëva, elle a dit Mathéo. On lui dit coucou à Mathéo. Coucou Mathéo.
Salut Mathieu, ça va? Non, non, ça va.
C'est pas mal,
Ah,
Thibaut.
pourquoi? Attends, toujours Thibaut. Un mec super en fait là.
Ah, c'est Thibaut, pas Mathéo.
Oh merde! Oh putain. On arrête.
Gênant.
Yeah. Now everybody's laughing, huh?
Wash your hands.
Sorry? What did you say? Hmm? Whatever. Okay, did you do it?
Almost.
Almost. You want me to wait a bit more? Let's do it together. So if I write this, the sum of the forces, I have to write it vectorially first, okay? The sum of the forces is, of course, T plus Fg, vectors, so there are pluses everywhere, is equal to mass times acceleration, right? And now what do I need to do? There's one step now that is important.
T equals to m times a minus fg.
Yeah, but before we do that, maybe we should go from the vector formulation to the scalar formulation, okay? We would like to have this equation with numbers. We would like to have T, Fg, and Ma. And the question is, what are the signs here? So how do we determine these signs? You remember that? We should take a convention here, right? We should take
FG is
a...
positive. FG is positive because the object is going, is falling.
Yeah.
So FG is positive.
Okay. So this means that we are taking as a positive direction, as a positive convection direction, the direction of going down, which is quite natural for an object which is falling. Okay, so Fg will be plus and T will be minus. Why in the course they took why they didn't take the same sign as me? Why the hell do they take the sign? The acceleration is pointing down, so it's positive. The tension is pointing up. Yeah, okay. So tension now minus Fg is equal to minus Ma. So the tension is going to be minus Ma plus Fg, which is Ma, mg, and so this is going to be, but it's wrong. Why is it wrong? Oh God, I hate that. mean, that,
Que tu es là? Je t'avoue.
no, listen, what I did is correct. I don't know how they did it, but what I did here is correct. T plus Fg is equal to ma. The positive direction is when going down, so T is negative, Fg is positive, so T minus Fg is minus ma. So T is minus ma plus mg, which means m times g minus a. Okay? Whereas they have T plus a. But anyhow, they are, okay. And in their approach, they're going to have an a which is negative, while we are having an a which is positive. So it's the same. Okay? So we have this expression of t now. And what do we do with that expression? Now we can put back this t into the equation we had before. Okay? So we had the work of tension is equal to minus the tension times the distance, and so it's going to be minus mg minus a times the distance. Okay?
Just a question, where does the flèche go?
Does the what?
La flèche, elle va où?
The arrow. From
ouais.
here to here. It disappears. Because I
I can't
decide.
see it, just can't see it.
You can't see what?
The big arrow.
Just
Yeah.
the right.
The snake arrow.
The one which is.
This one.
Yes.
Yeah.
Ah, it goes up here.
Oh, well.
Okay, to say that this value that we computed for t, it's actually the value we wanted to compute here. Yeah, sorry. Well, I can also have the whole page on the screen, but then it's going to be small. Okay, so the work of the tension is minus mg minus a times d, and now we can compute that. Okay, what's the cosine of the angle? Well, here I didn't insert the cosine of the angle. It's minus sorry, it's oh god, I'm doing shit. It's minus t times d, and t is m times g minus a times d. I already took into account the angle. Yeah, because we already took the angle in account up there. Okay, so now we know that a is how much? A is g over 5. Okay, whereas you see that in the course they take minus g over 5 for a, so finally the sign ends up being the same. Okay, and so we have minus the mass, which is 500, times g minus g over 5, which is 4g over 5. Okay, it's 5 over 5 minus 4 minus 1 over 5, it's 4 over 5 times d, and if I compute this, I get to this result here of minus 47 kilojoule. Okay, you see they have the same sign at the end because they do the trick with the angle at the end, whereas we did it at the beginning. Okay, and now you can observe one thing. If you compare the work of the tension to the work of the gravitational force, you think it's the same or not? Remember, in the previous page we computed the work of the gravitational force. We find 58.8 kilojoule, and now we compute the work of the tension and we find 47 kilojoule. Okay, minus 47. So you see, these two works, they are not compensating each other. Why? Because the accelerator, the elevator is still in motion. Okay?
So to complete the whole, we have to do 58.8 plus
Yes, and this will give you what in the end?
the net force.
With this we will be able to compute the velocity of the elevator at the end of the fall, because we know the energy before, we know the energy after. Okay? So now we answer question C, and question C is, it's on top on the right, what is the work done on the cab during the fall? Okay, work during the fall. What is it going to be? It's of course the work of the gravitational force plus the work of the tension, right? And now let's put in the numbers. The work of the gravitational force, it was 58.8, and the work of the tension, we just computed it here, it's minus 47. Okay, and this is all in kilojoules. Okay, so 58.8 minus 47 is approximately 12 kilojoules. Okay, so during the fall, actually the gravitational force gave a lot of energy to the cab, and the tension, it took some energy from this cab, so that in the end the energy that the cab is acquiring during its fall is only 12 kilojoules. Okay? And question D now is, what is the cab's kinetic energy at the end of the fall? Okay, this I will let you do. How would you do this? How can you compute the final kinetic energy? Which equation do you use?
The Torricelli, like the one we used.
Yeah, okay, we don't call it Torricelli. It's an equation of conservation of energy, but indeed it looks like Torricelli. It's Kf minus Ki is equal to the total work. Okay, this is the energy that this is the formula that you are going to use to compute the final kinetic energy. I let you do it. Don't forget that the cab was already moving at the beginning of the experiment. Okay, it was already moving downwards, so there is an initial velocity. Okay? Or not okay?
Almost.
Hmm?
Almost.
Almost?
Yeah.
Okay? So let's see. Kf is 1/2 mvf squared. Ki is 1/2 mvi squared, and this is equal to the total work. So the total work is this guy that we computed here. This is the total work. Okay, so this is equal to 12 kilojoule. Be careful not to forget the K, because it's 12,000 actually. Okay, Vi, we know it, it's 4 meters per second. Vf, we don't know it, but we can compute it with this. Okay, well, let's compute the initial kinetic energy here. What is it? Is 1/2 times 500 times 4 squared. Okay, so that's 16 divided by 8 times 500, it's 4,000. Okay, here we have 12,000 joule. Okay, so what does this mean for the final kinetic energy? It's how much?
4,000 plus 12,000.
Exactly. Okay, so here we have 16,000 joule. Okay, so you see that the initial kinetic energy is quite low because the elevator is falling at 4 meters per second, which is not a very high speed. And then we apply a net work on this cab, which is positive. It's 12,000. Why is it positive? It's because the work of the gravitational force is larger than the work of the tension. Okay, and so these 12,000 joules that we are given the elevator cab during its fall, it's going to be now, we are going to find it now in the final kinetic energy. Okay, and so the final kinetic energy being 16,000, we can now compute the final velocity. The final kinetic energy is 16,000 joules. So the final velocity, it's 2 times 16,000 divided by the mass, which is 500, square root. Okay, they don't do this calculation in the course. So let me compute that thing with my stupid calculator. This is 32. Oh God. This is 32,000 divided by 500. 64, and the square root of 64 is 8. Okay, so indeed the cab is going faster after a 12 meters fall than at the beginning, because it received more work from the gravitational force than it gave to the tension. Okay?
I just have a question.
Yeah.
Why are the units meters per second squared?
Because I'm sick and I'm not awake yet. It's meters per second. Thank you. Okay, we are going now to go into something else. So if you have questions about all these work, you can ask them now. Well, anyhow, we are going to continue with work in a moment, but now I want to introduce a notion which is new in this course, which is the notion of power. Okay, this is something you hear all the time it's a very common word, but in physics we have a very precise definition of that actually. The power is the energy divided by the time. This is the definition of the power. Or you can write it also as the work divided by the time. The work the system can produce divided by the time. But the work is a form of energy, so these two formulas are okay. Okay? So the power is a quantity, a scalar quantity, that expresses how fast you can produce energy. Okay? If I have a very powerful car, I will be able to increase the kinetic energy of my car very fast, and so the acceleration will be much stronger than if I have a car with low power. A car with low power produces less energy per unit of time, and so it's going to accelerate less, right? Okay, now what's the unit of power? The unit of power is of course joules per second, because it's an energy divided by a time. Okay, and the joule per second, we call it the watt. And this name was given in honor of James Watt, who was a famous scientist in the 19th century. Be very careful, because the watt, we write it capital W. Okay, and so in this chapter you are going to have two capital W's. Okay, one which is work, and the other one which is the unit of power. And these two, they write the same, but they are different things. Okay, try not to confuse them. Okay? Now I'm going to do the connection with one thing which you also heard. It's the horsepower. In French we say le cheval ou le cheval vapeur. Horsepower égale cheval. Initially it was cheval vapeur, but now people say cheval. Okay? So the cheval is a unit of power. If you have a power with 200 horsepower, it's going to be more fast. It's going to accelerate more than a car with 50 horsepower. It's also going to be more expensive. Okay? Let's see this relationship. I would like to illustrate that. This is not done in the class. Okay? Let's see how the power of a horse could give us something like that. Okay? Because this unit is really historical. The horsepower, it was a unit used at the time where we had horses to power our factories. Right? You know, I guess you studied the Industrial Revolution in history. Before the Industrial Revolution, work was mainly done by humans and animals, and during the Industrial Revolution, we introduced machines, motors, which would run the factories. But before that, a factory, if you needed power in a factory before that, you would do something. Oh God, I have to draw horses now. It's complicated to draw horses. Okay, you had, yeah, don't laugh. Okay, before I have to draw them in the right orientation. Voilà. Before the Industrial Revolution, if you needed to power a factory, you would have like 3 or 4 horses walking in a circle, and then this was making this axis move, and you would transmit this power to all the factory to make machines work. Okay, at the Industrial Revolution, the horses were replaced by a motor, but the horses, they remained as the natural unit for power. Okay, So 1 horsepower, let's try to estimate how much it could be in watts. So let's take a horse. I should take drawing classes. We don't have drawing classes when we study to become a teacher. Yeah, I'm sorry, okay? Okay, so we have a horse, and let's imagine that this horse is pulling some mass up from the ground. Okay, here there is a rope, here there is a pulley, and so the horse is pulling up this mass. Now I'm going to ask you, give me a time for a horse lifting a mass of I don't know which mass, a mass of 500 kilograms by 1 meter. How much do you think? It's an approximation, it's a game we're playing. How many seconds do you think a horse takes to lift 500 kilos by 1 meter?
2 seconds.
Huh? 2 seconds? 2 seconds. Yeah, it sounds a bit fast, but 2 seconds. Okay, let's try 2 seconds. Okay, so now if I want to compute the power of this horse, what should I do? Okay, the power is the work divided by the time. So the time, we have 2 seconds, as you said, and the work is what? What is the work that this horse is doing? It's the gravitational force times the distance, right? And the angle is 0. The angle is 180. Okay, the work is minus. Don't worry about the signs. Okay, so this is going to be mg times d. So m is 500, g is approximately 10, and the distance is 1. So this is 5,000. 5,000 over 2 is 2,500. Okay, so indeed the time you gave me is kind of fast. Okay, it doesn't take 2 seconds to a horse to lift a mass like that. It's quite heavy. And now if you want to obtain something like what we have in the course, you should divide it maybe by 8. If you take 8 seconds, 5,000 divided by 8, that's how much? 5,000. Oh God, 5,000 divided by 8 is 625. It's the correct time for a horse to lift a mass is about maybe 7 seconds, because what we have is this 1 horsepower is 746 watts. Okay, but you can estimate the power of a horse by doing this, by computing the work it's doing, by estimating the time it takes for him to do this work, and so this gives you the power of a horse.
I have a question.
Yeah.
So you are telling me there that a car of 1 horsepower would take 8 seconds to do 1 meter. It's a bit long, no?
You think it's too long? You know, the definition we have is 1 horsepower is 746 watts. Okay, this is the current relationship between these two values. Actually, I never tried to do the experiment with a horse, a real horse. If you have one, we can do it. Okay, but yeah, a horse can lift a mass of 500 kilos in about 7 seconds. Okay, this is by 1 meter. This is the power of a horse. It's just a question of units. I'm just trying to explain you where the horsepower comes from and how we can get an estimation of it. Okay? Okay, listen, we didn't do the break, so I'm not going to go until but it's until 35. Okay, but I prefer to let you do the exercise. Well, try to do exercise 2 down here. No, there's one thing I didn't tell you yet. It's the other unit which is important. It's the kilowatt hour. Okay? What is the kilowatt hour? A kilowatt hour, this is what your parents pay for electricity. Okay? There is a certain price per kilowatt hour. And what is this kind of unit? Well, we saw that the power is the energy divided by the time. This means in terms that the energy is the power times the time. Okay? Let's say we have a power of 1000 watts. Let's say this is going on for 10 seconds. So this is going to give you an energy of 10,000 joules. Okay? And now if you look at this unit, the kilowatt hour, you can see that it would be a very good unit for this, because kilowatt is the unit for P and hour is the unit for time. Okay? So actually the kilowatt hour is a unit of energy. Okay? It's a power times a time. It's a unit of energy. And it's normal that your parents pay for energy, not for power. They pay for the total amount of energy they receive, and it doesn't count whether they used it fast or they used it slowly. They just use a certain quantity of energy. Okay? Now, my question is, 1 kilowatt hour is how many joules? Okay? So how could we compute that?
It's written.
Sorry?
It's written.
Yeah, I know it's written, but you're not supposed to read the course, okay? So the kilowatt is the power, the hour is the time. So the energy is the power, which is 10,000 watts, okay? 1,000 watts, God. 1,000 watts times the time, which is an hour. And so we need to write the time in seconds, because the standard unit for time is seconds. Okay? And so you find now 1,000 times 3,600. You find that 1 kilowatt hour is 3,600,000 joules. Okay? And 1 kilowatt hour costs you about 20 cents, I think. Something like that. 20, 30 cents. Okay? Yeah, so it's much, much, much cheaper than gas or chemical energy, clearly. Okay, we did not do the break. I will stop a bit before, and I'm asking you for next time to do exercise 2 on page 20. Okay, what is exercise 2 on page 20? We have 2 cars. Exercise 2 on page 20. We have a road which is going up to some mountain pass. What a nice drawing I'm doing for you. The road is going up to the mountain pass. Okay? And the valley is at 550 meters, and the pass is at 2,000 meters. Okay? That could be the Simplon, which is at 2000 meters. And we have two cars going up this path. Okay, one has a power of 250 HP, and the other one has a power of 180 HP. And I would like you to compute the time difference which will separate them when they arrive on top, using their maximum power, of course. And of course you neglect friction for that. Okay? Try to do it. You have to play with the power is equal to the work divided by the time, and the work is the gravitational force times the distance. And now this work, you can take the distance to be just the vertical distance between 550 and 200. Okay, but I would like you to do it, and so I'm going to write that devoir pour le next week is the 31st or the 1st of May? 31st. Okay.
Oh, juste regardez ma gomme. C'est pas trop chou.
Good.
Il y a d'entre vous qui passe un exposé en français aujourd'hui?
Je crois qu'il y a l'heure et... un exposé dans 1 heure.
So just one question. This test.
Oh, pas bonne chance, hein.
Gros, je suis trop dans la merde.
Listen to me for another minute. This test, we cannot do it. Okay, the test which we had planned for last week. And there will be no tests at least until the end of the Easter vacation, when we go back to school. But if you want my opinion, we will not be back in school before something like 2 months. Okay, so it's going to be a mess. So now I don't know yet how we will deal with that. Maybe one thing I can do is to give you homework, something that you do by groups, but I need to think about that. I need to write something, etc. Or well, for the end of the year it's not complicated, we can do orals. Okay, if we cannot meet to do written exam, yeah, we could do orals for the semester test. Why not? Do you have a better idea?
No, it's just...
It's a mess. What can I tell you? We have to deal with the situation, and so doing orals is a way which we can do work in. Okay.
I just had a question.
Yeah.
If we can't go back to school until July,
Mm-hmm.
Will the school year be cancelled or?
No, I don't think it will be cancelled. In this kind of cases, if the student could not work, I guess the criteria for passing the year will be lower. Okay, I don't think your school year will be cancelled and you will have to redo it. That's excluded, I would say. But I'm not among the people who take this kind of decisions, so I don't know. Okay, but if the situation lasts for another few weeks, there will be decision made much higher than me, and we will apply these decisions. I don't know at the moment. I think it's going to last pretty much, but I don't know. Okay?
Okay.
Okay, so listen, I have recorded today's course, so I will put the recording on YouTube. I have a YouTube channel. If you want to watch it again, you can. And those who could not know, today everybody was with us, okay? But if you want to watch it again, I will put it on YouTube. And I will send you an email with the YouTube link via Classrooms. Okay? So, but we meet next week, and during that time, be good boys and girls, and take care of yourself. Okay? Okay. Bye-bye.
Bye.
Bye.
Ciao les loulous.